Welcome. Today, we're going to pull back the curtain on one of the most important families in all of chemistry. Now, you might think you know them, but trust me, there's a whole world of fascinating characters beyond the one you're probably thinking of.
And yeah, this is the one, the star of the show, the one everybody recognizes, ethanol. It's the alcohol in all our alcoholic drinks. For most people, the story pretty much starts and ends right here. But for us, oh, this is just where the fun begins.
Because what if I told you that ethanol has this huge, sprawling family of chemical relatives, and these relatives are, well, they're wildly different. I mean, some are powerful antiseptics we use to clean cuts. Others are literally the reason bananas and perfumes smell so sweet, and then you have some that are so stable and stubborn they barely react with anything. So how can one family be so diverse?
Okay, let's get into it and actually meet them. We're going to get to know the entire hydroxyl family. That's the proper name for the group of compounds we just call alcohols and phenols. So first things first, we need to understand what makes them a family in the first place. What's the one shared feature they all have that goes way beyond just the drinking glass?
It's this right here, the hydroxyl group. It's just a simple little setup of one oxygen and one hydrogen atom. We write it as negative OH. This little group is the family signature. If you see a carbon-based molecule with one of these stuck on it, then congratulations, you've just met a member of the hydroxyl family.
And that tiny OH group, it gives the whole family a kind of superpower, hydrogen bonding. It lets these molecules, hold hands with each other. This stickiness means it takes way more energy to pull them apart and turn them into a gas, which gives them these surprisingly high boiling points. It's also what lets the smaller family members dissolve so easily in water because they can form those exact same bonds with water molecules. Pretty cool, right?
All right, now that we know the family name, let's meet some of the individuals. In the world of simple alcohols, we can basically classify them into three distinct groups. It's easiest to think of them as three different siblings.
First up, we've got the primary alcohol. Now look closely at the carbon atom that's holding onto that all-important OH group. In a primary alcohol, that carbon is only connected to one other carbon group. That's it. It's the simplest arrangement. Next is the secondary alcohol, and you can probably guess the pattern here, right? The carbon atom holding that OH group is now connected to two other carbon groups. So it's getting a little more crowded, a little more complex. And finally, we have the tertiary alcohol. Here, that central carbon is attached to three other carbon groups. It's totally surrounded. Now, this structure is absolutely crucial. This isn't just a minor detail. As we're about to see, this dramatically changes how this sibling behaves. Let's see how that structure affects a totally different property, acidity. Most alcohols, like our friend ethanol, are incredibly weak acids. But there's another branch of the family, the phenols, where that minus OH group is attached directly to a really special carbon structure called a benzene ring. And that changes everything. See, it all comes down to stability. When an alcohol acts as an acid, it gives up a hydrogen and gets left with a negative charge. In ethanol, that charge is just stuck there on that one oxygen atom, which is super unstable. But in phenol, that special benzene ring can pull in that negative charge and spread it out across the entire molecule. This makes the whole thing way more stable. And because of that, it's much more willing to act as an acid. And when I say much more willing, I mean it's not even close. To put a number on it, phenol is about 100 million times more acidic than ethanol. 100 million. That massive difference comes down entirely to how the molecule can spread out that charge and get stable. You see the pattern? Structure dictates function.
Okay, now let's look at one of the family's most impressive talents, their ability to completely transform. We're talking about a reaction called oxidation, and this is where the differences between our three siblings really start to shine. A primary alcohol is a total master of transformation. With just a gentle oxidation, you can turn it into something called an aldehyde. But if you hit it with a stronger oxidizing agent, it transforms all the way into a carboxylic acid. I mean, that's two totally different products from the exact same starting point, just by changing the conditions. And this just brilliantly shows why that structure matters so much. Remember our tertiary sibling, the one where the central carbon is completely surrounded? Well, that structure acts like a shield. There's no hydrogen atom on that central carbon for the reaction to grab, which is a necessary step for this kind of oxidation. So it just doesn't react. It completely resists the transformation. Now keep that in mind because that is a major clue for later.
Now, the family has other talents too. When you react in alcohol with a carboxylic acid, you get a whole new type of compound called an ester. And why should you care about esters? Well, because they are the molecules behind many of the most wonderful smells and flavors in the world. They're small and light, so they can float up into the air and reach our noses, giving us the scent of everything from bananas to apples to flowers. That's all hydroxyl chemistry.
Okay, so now it's time to put all this knowledge to work. Let's imagine we're chemists, and we've been presented with a challenge. A little chemical case we need to solve.
Picture this. You're handed 3 unlabeled test tubes. Each one has a clear, colorless liquid inside. You're told one is a primary alcohol, one is a secondary, and one is a tertiary. They all look exactly the same. So how on earth can you tell them apart? Well, the answer lies in those special talents we just talked about.
We can set up a sort of chemical lineup using our oxidation test. We take a sample from each test tube and add this vibrant purple chemical. In 2 of the tubes, that purple color is going to vanish as the alcohol gets oxidized. But in 1 tube, the purple color stays. That's him. That's our tertiary alcohol, the one that resists oxidation.
That simple color change is the smoking gun. We have positively identified one of our mystery liquids, but we still have 2 suspects left, right? Both the primary and the secondary alcohols made the purple color disappear. So how do we tell these 2 apart? We're going to need one last clue.
And the answer isn't in the reaction itself, but in what it created. Remember, the full oxidation of a primary alcohol makes a carboxylic acid. The oxidation of a secondary alcohol makes something called a ketone, which is neutral. So we take our 2 remaining colorless solutions from that first test, and we add a simple weak base, sodium carbonate. The solution that came from the primary alcohol will now fizz and produce bubbles of carbon dioxide because an acid is reacting with a carbonate. The other one does nothing. Case closed. So you see how these really subtle differences in structure between the 3 siblings give them completely different chemical fingerprints, and this brings us to a final thought. We've only met a tiny, tiny fraction of the hydroxyl family. So if structure dictates function disprofoundly for these simple molecules, just imagine what incredible properties and hidden talents might be locked away in the thousands of more complex alcohols out there just waiting to be discovered.